section 5.3, we're looking at the fundamental theorem of calculus. To begin, we have gotten pretty good at thinking about the definite integral as meaning the area underneath a curve. And so we're going to create a function based off of that. So we start with a definite integral that doesn't have an upper bound. So we usually integrate from a to b, but I'm going to define this from a to x. I'm going to let that upper bound vary, and so I can create an area function, not just an area as a value, in terms of that bound x. So if I plug in various bounds, I'll be able to change the region, and that will be useful to us in order, if I wanted to find area over a to b, and then another one over a to c, and another one over a to d. If I have that same area as a function, I can call that area function by just changing the bound. It's going to be useful for us to be able to do that. Okay, so let's take a look at how this is going to work the next page, and then we'll get into that fundamental theorem of calculus notation as well. So first, I'm defining a of x to be the area function that is the integral from -1 to x f of t dt, and b of x to be the area function that's from 3 to x f of t dt. These are two specific area functions for f. They have different start points, right? So the first one starts at -1, and the second one starts at 3. All right, now I can call these areas as functions. And so if I want to evaluate a of 5 first, a of 5 is going to be the integral from -1 to 5. And so if I'm going from -1 to 5, we're going to have this area is negative, so we're going to have -27 plus 3. So we're going to end up with a net -24 for that area. So we're going all the way to 5. We have negative, positive, negative areas. Okay. Now b of 5 is the integral from 3 to x, so 3 to 5. So b doesn't start until 3. So if I went from 3 to 5, that's this area, this middle area where the area is 3. So b of 5 is 3 and a of 5 is -24. What do I notice about the value of a of x minus b of x? Okay. In this case, if I look first at a of 5 minus b of 5, a of 5 minus b of 5 is -24 minus 3. It gives us -27. So when I subtract these two areas, I get back to the first area. So it's back to just the area of the first region. And so that would be from -1 to 3. So what I'm noticing is that our a of x minus our b of x, in general, the x's were canceling out up there and getting us back to the integral between the two regions. So we can generalize that and maybe discover a pattern. If I'm looking at the difference of these two integrals, if the x's are subtracting off right here, try it for a few more regions until you're confident, but this is turning into the integral from -3 to 3 of f of t dt. So it's coming back into that constant because the upper x bound with that negative is subtracting off that other upper x bound. Oops, sorry, I need to push my paper up. So those were canceling off, and they were going to become the -27 in all cases. All right, in the bottom of the page, if we have the function b of x over 3 to 5, what's going on there? So b of x is the area function, and on the interval 3 to 5, it would start at 3 and start shading. And so it would reach a larger value and reach a larger area value and continue to reach a larger area value. Even when it gets over to this edge, it's still adding on area. So it's definitely an increasing function because the area value is increasing the further that you're able to shade it as you approach larger values of x. So it's an increasing function. The b of x function from 5 to 9, okay? So the b of x function from 5 to 9, b still starts at 3, so, but I'm looking at it from 5 to 9. So we're looking at it down here. So we had some positive area. Now we're taking, and well, the new part is that we're taking these negative areas and adding on these negative areas. And so we're adding larger and larger negatives, so we're going to start canceling out that positive. So that positive value is going to be subtracted, subtracted, subtracted. It's going to be decreasing over this region as we increase the portion that the area is negative. Okay, the ideas of the area functions lead to, let's see, some important points. See the text for proof. So the derivative of the integral of f is f. They're inverses. This may seem obvious, and that's partly what this theorem says, but if you do the derivative of the integral of f, you get back to f because they're inverses of each other. So the derivative and the integral undo each other. So part 1 of the fundamental theorem of calculus says just that if we define the area function as the integral from a to x of f of t dt, like we did before, we can now take the derivative of that area function, a prime, or d dx, of the integral, and we should get f of x back out. So the derivative of the integral is the original function. Now it's in terms of x instead of t because I integrated this, I replaced with x, and I differentiate back in terms of x. But I'm getting the f of t function back in terms of x, f of x, because I've changed my variable. But the derivative of the integral is back to the original function. Now, that theorem, while useful, is not quite as fun as its counterpart, the fundamental theorem of calculus part 2. And this says that the integral from a to b f of x is capital F being one of the general antiderivatives, evaluated at b, minus capital F evaluated at a. This is going to be extremely powerful in terms of evaluating definite integrals. Okay, so we're just going to make some notes about this notation down here and a third notation for it right here. So this is our second fundamental theorem, and we have our upper and lower bounds. So upper and lower bounds are the a and the b. Then we have f of x, which is the integrand. And then they're both with respect to x, so x is our independent variable. And then dx by itself, that would be for x, just the independent variable there. Dx itself is the differential in terms of x, and they have to match, so it's got to be f of x dx. And then capital F is the antiderivative. But we're actually evaluating it at a number. So we're plugging in b and plugging in a. So this is a number. It's not a function anymore. We evaluate it at a point. This is a number. Okay, and then the shorthand for this notation is f evaluated at top bound minus bottom bound. That's some shorthand that's going to ask you to evaluate at top bound and then minus bottom bound. So normally I actually would probably squeak this step into the middle. That's usually what we write after we have the integration. Now, what we need to keep in mind as well, for a little extra note at the bottom, is that we are finding that capital F of x with the definite integral. So it's the antiderivative, right? And then we're going to, once we have the capital F of x from the definite integral, we're linking it to from the indefinite integral, we're linking it to the definite integral by evaluating our new function, our antiderivative function at those two places. Okay, that's the link between. We've been using that same notation. Why have we been using that same notation when we haven't done any antiderivatives? And now we're going to do some antiderivatives. Okay, so looking back at this graph, we have done the area of this a couple of times in previous sections, but different bounds of here. We could do this one. We could get the area geometrically. What we're going to do instead is get the area through the fundamental theorem of calculus, the part 2. So the first thing to do, I'm going to write it down. I'm looking at a definite integral from 0 to 5 of 3 minus x dx. The first thing to do is to find the antiderivative. So if I did the indefinite integral, ignore the bounds for a minute, then I would have 3x minus x squared over 2 if I add 1 to the power divided by the new power. Then I put that vertical bar right there to say evaluate at, and then I have my bounds of 0 and 5. Now the definite part comes in, or the fundamental theorem of calculus part comes in, where I plug in top bound minus bottom bound. Okay, so we evaluate this and get 3 times 5 minus 5 squared over 2 minus quantity, plug 0 in, 3 times 0 minus 0 squared over 2. And this simplifies to, that's 15 minus 12.5, so that simplifies to 2.5. So we should have 2.5 for the area, and if we did it geometrically, we should get the same thing. We might have done the exact same one earlier. I can't recall if we did the same bounds on it or not. So look in the previous section to see if that's the same thing we got, or just do it geometrically and see if the area of these two triangles adds up to 2.5. I'm sure it does. All right, so we can do this in other cases that are not geometric, like this one, not geometric. And so I can graph, oh, it says including a graph the area, so I didn't graph the area, so we'll go back and do that. So 5 here, so the area is just this shaded region, right? Just wanted to make sure we saw what region we're actually graphing, what region we're actually finding the area of. So we could do that one geometrically. Can't do this one geometrically because it's not a geometric shape. It's the integral 0 to 4, so with 4 as my bottom border, and 0 as my upper, or the border on the left and the border on the right here, we want the area of this combined region. The bottom part of it over on the 2 to 4 part is going to be negative, and the 0 to 4 part up there is going to have a positive region. I think the whole thing is going to be negative, so it looks like there's more space down in the negative quadrants than there were in the positive. So let's find out. Okay, so we're going to integrate 0 to 4. Our function is 4 minus x squared dx. The first thing we do is find the indefinite integral, or the antiderivative. The antiderivative of 4 is 4x minus x cubed over 3. Add 1 to the power, divide by the new power. That bar means evaluate at 0 to 4. So I plug in my bounds, always upper bound first. So top bound goes in first, then bottom bound. So we're going to start with 4 times 4 minus 4 cubed over 3 minus 4 times 0 minus 0 cubed over 3. That's 0 again, so I'm just concerned with the 4 squared minus 4 cubed divided by 3. So if I calculate that, I just use a calculator to get that, but 64 minus, I can't remember what 4 cubed is, but 4 cubed is 64, so that's 16 minus 64 thirds. Anyhow, 16 times 64 thirds minus 64 thirds comes out as negative 16 thirds. So it is negative. I was guessing that it was going to be negative because it looked like this region was larger, and so that matches what I had expected. So it's negative 16 thirds.